So it's 2 blocks, 3 blocks. For any partition, I can identify any partition as a matrix. It's an n by n matrix, where I define the ij entry to be 1 if I and j are in the same equivalence class and 0 otherwise. So, for example, this would be the matrix representation of this partition here. And so, once we represent partition as matrix, we can think about taking the permanent of a partition or applying this function to a partition. And if we do so, the expression for this, we have a nice simple expression, which is sum as a product over the blocks of alpha, and we have a rising factorial of the cardinality of the block. So this is alpha. So over here, the permanent of the block diagonal matrix is the product of the permanents of the blocks. We would have alpha squared plus alpha from here times alpha. So this is just alpha plus 1. Substantial identity, so this is everything so far you could easily do yourself. For 2 matrices A and B, I'll define the Hadamard product A dot B. This is just the element-wise product. So for 2 parameters, so now for 2 parameters, alpha and beta, I have the following observation. The permanent, that the alpha beta permanent of M is alpha times beta. So the definition of the permanent is sum over permutations. I can express this as a sum over partitions. Specifically, set partitions. So talking about set partitions always, not today. I won't talk about partition of an integer. Beta, following factorial, the number of blocks. Population as a statistician in population genesis. And this is a probability distribution on partitions. And the size probability is as follows. So there's 2 parameters. The parameters are alpha and beta. And the size probability of partition pi according to this rule. So we have a rising factorial involving the number of blocks. We just have a normalizing constant that involves the size of the partition, and then we have some product over the block sizes. And if you were to look this up, so if you wanted to look this up in Wikipedia or something, actually it would go by the name, I think it was distribution you can get. We're doing sampling formula, and also there's something called the Chinese restaurant process, which is a process used in statistics that's closely related to this distribution. So I was working with this distribution.
The microscience don't make it negative.
No, it's a weird way. This is how it's usually written, the most compact way to write it. So this minus alpha is in a rising factorial, so it's going to come out as minus alpha, and the minus minus. Okay, no. Yeah, so that's, and this is going up. Oh, I should write the parameter space, which is this is we need alpha to be between 0 and 1. In that case, theta has to be bigger than negative alpha. Or if alpha is negative, theta has to be equal to minus a positive an integer multiple of alpha. Okay, so that's the region on which this is a proper probability distribution. So I was studying this, and I was looking at this distribution, and I see all these rising factorials, and I note the connection over here, and I was curious whether or not these could be re-expressed, or these were actually just some permanent, in a very special case of a permanent. So this suggests another distribution, going back to the identity that I showed you here. As long as everything here is positive, this part gives you the normalizing constant of the probability distribution. So we have another family with 3 parameters.
So this is a kind of
If you want to call it that, sure, yeah. But I can't do that, so you can start. So this becomes interesting because it has this extra parameter. It's a little bit more complicated, but just to know the connection here is that if we take alpha to minus alpha, beta to minus theta over alpha, and m to the matrix of all the Ewens alpha theta distribution. So a way to interpret the Ewens distribution in the study of random partitions and statistics, the Ewens distribution has a property that's called exchangeability. And what that means is that if this is going to assign equal probability to any 2 partitions that are so if you just keeping the structure of the partition, keeping the block size the same, but switching around the elements, then they're going to get the same probability of this distribution. So one way to interpret that, especially in light of this more general family, is that this matrix M somehow gives us a description, it's a parameter that's describing the way in which different particles interact with one another. And a matrix of all ones is like a homogeneous environment in which they interact. More generally, we might not have that, so we have this family of distributions. Okay. Let's see. Another consequence so one further consequence. Is that when we realize the connection, the expression of the determinant in terms of the alpha permanent, we can first I'm just going to get -1 here. We can express the alpha permanent as a linear combination of determinants. But, so, we talk about computational complexity. The determinant is easy. The permanent is hard, and the alpha permanent is believed to be even harder, or at least as hard, for alpha other than 0 and -1. So we have something easy, something hard, but there's a lot of terms in this sum, so this doesn't seem to help us right off the bat. One possible way that this might help us, and I'll come back to this a little bit later, is that if we take k to be a positive integer, then the negative k permanent, I guess I still need this, -1. That's this expression, which is the same expression, but since we have a problem factorial here, this is going to get zeroed out for any partitions with more than k blocks. So there are fewer terms in this expression, still a lot. So in general, this is now a sum over, this can be simplified to a sum over partitions having at most k blocks. And this asymptotically is like k to the power n, so there's still a lot of those terms. But given the relationship between the -1 permanent and the determinant, and maybe a slightly simpler expression here, I wonder, so first question I have, and this is admittedly this is an ambiguous question, but is whether or not there is is there any interpretation of these -k permanents as generalized determinants or something like that. So I won't say what I mean by that, but I'm curious. So for example, the determinant has an interpretation in terms of the volume. In terms of volume, I wouldn't expect that these negative k permanents have such a thing, but what is the connection there, if anything? And so if that brings us back again to what was originally motivating the study of these objects, the similarity to the determinant. Okay. So the second identity that I won't talk much about because I don't know, but it doesn't seem to lead me very far, is the permanent of a product. So you know that the determinant of a product is the product of the determinants. Not the case for the permanent. This is a sum over n tuples of integers 1 through n, and they can repeat. So if they didn't repeat, they would just be permutations. But this is over all possible strings. And it has a little bit of the way I write it is a little bit strange. But where Vx, so Vx is a matrix whose ijth entry, whose ith row is the xith row of V. So there can be repeated rows in this, there will be repeated rows in V, but in the case of alpha equals -1, this is the determinant, related to the determinant. So we know that the determinant of a matrix with 2 identical rows is 0, so this is going to only count terms in which all of these indices are different, and that's just a permutation. And so we get back the case where the determinant of a product is the product of the determinants. But in general, for alpha not equals -1, this is not true. Okay, finally, and this is the one that has me, I think, leads to the most interesting observation of today, and raises the most questions, of which I don't have the answers, but it's certainly worth exploring if you're subsets of n. This is where so IS of ij, this is a diagonal matrix where there's going to be a 1 if I equals j and I is in S and 0 other. So this is the identity matrix, but I only count the diagonal entries that are in S. So when I multiply it by A, all I get back is just the part of A that corresponds, that's indexed by S, and then I add that to the part of B that's indexed by X complement, and I get a whole matrix out of that. Okay. So 2 observations. First, so these two observations, and the reason why I felt inclined to talk in the seminar was these were observations I originally made just by playing around on the computer, testing out computing different things and seeing that these relationships seem to hold, but then afterwards realizing that actually I should have done this a while ago because they can be seen as consequences of what I'd done before. But they do give some, they seem a bit suggestive of where they might lead. So the first one is just that for any matrix, the alpha permanent is a sum of n terms where there's some constant. So it's a combination of some constants that don't depend on the matrix. Times these minus k, where the form of these coefficients have a bit of a complicated form. I'm not sure if hopefully don't make a typo here. I'm not sure if it can be written in a nicer way, but it does have a formula. But for alpha equals 1, so just the ordinary permanent, these are binomial coefficients. So I'm able to express the arbitrary alpha permanent as a linear combination of only n terms of these minus k permanents, and that's again why I asked whether or not these, or why I think that these minus k permanents are somehow special. Another thing I should have suggested, or should have mentioned up here, was when I look at these identities, I tried to use this identity in particular to see whether or not that one, this one. I mentioned in applications we often want to approximate. Well, we can't compute this, so we often want to approximate this value. So this looks potentially promising as a way to approximate this, since I have something here that I know that I can compute, and there's certain statistical techniques that might be worthwhile, that might be useful here. And it seemed from my initial investigation that the case where k was an integer, some of the techniques I was trying out work much better. They're much more accurate than in this case, and it makes sense because there's fewer terms. And so here the idea would be if I can approximate these, well, then I can approximate these because I know I have an explicit relationship between them. But still, I haven't come across a foolproof way to approximate these. Okay. And the last one is coming from this here. If I consider the case, so what I'm going to do is consider the case A to B, lambda times the identity, B to B, my matrix M, and see what this looks like when I take the alpha permanent of this matrix. Right? So this is like a characteristic polynomial. Right? This is the characteristic polynomial when we're talking about determinant. Right?